In today's class, we will discuss a new topic, which is random access memory. Okay. Random access memory. You might have heard this in your lower classes itself. Okay. So basically, when you are doing any operation in your system, this RAM or random access memory. Okay, this one is C double C here. We need random access double C. Okay. So in this random access memory, if you consider a system, computer system, let us consider pictorially. If you are having your software which is stored in the hard drive, okay. So this is your hard drive. Program stored in this hard drive. I don't know how many of you are familiar with this hard drive. Okay, so this one will be connected with this RAM, random access memory. This is your RAM. This is also we can call it as RAM. So this is connected with this random access memory like this. Okay, so when you are starting your computer system, or when you are starting any program in the computer system, actually this RAM will fetch corresponding data from the hard disk. Okay, from that corresponding memory location, and that will be taken by the RAM, and the execution of that particular program that will happen within this RAM. Okay, so while execution, the data or the program will be running in this RAM, random access memory. So CPU will take central processing unit. CPU will take CPU will give information to this RAM for execution of any program. Okay, and if suppose you are if you are opening the WhatsApp, for example, if in your mobile phone, okay, so the stored program that will be in your hard disk, that the application will be stored or installed in this hard disk in some, okay, and that will be loaded into this RAM. Okay, when you press your WhatsApp icon on your mobile phone, when you touch on that, so that will be loaded in this RAM. Okay, and from there onwards, the application or that particular software will be running in this random access memory. Okay, and when you are pressing the WhatsApp icon, CPU sent information to this hard disk as well as to this RAM, and that will fetch data from the hard disk where you stored your WhatsApp data, and that will be loaded into this RAM, random access memory, and RAM will execute that particular program or operation. Okay, so in that case, all the operations will be executed in this RAM. Okay, so we can say that any of the software or program if you are running, that will be running within this RAM. Okay, so it will take data from this hard disk and it will run. This is the basic operation of any program running in your system or in your mobile phone or anything. So in this case, suppose if you are running many operations, many programs at the same time, in such conditions, this RAM memories will be, in sometimes it may not be enough. Okay, so for example, if you are having a 2 GB RAM, 2 GB RAM, then in that case, suppose if you are running this RAM with some 10 programs, okay, and that each of these programs are having, let's say, some 200 MB, okay. So in this case, it can run because it is maximum. It can go up to the. I'm talking about the memory required for this 10 programs. Okay, so each of this program taking 200 MB from the RAM for running or execution. So 200 MB per program. We are having 10 programs, so you have 2000 MB used, so that your 2 GB is over. Okay, 2 GB memory is over. Now if you want a 11th program, which is also, you want to run this 11th program, then this RAM will take some time, because this maximum capacity is 2 GB. Okay, if you are running more programs, and if it is exceeding this limit, then that program may not work smoothly. Okay, so then you have to wait sometimes it will be loaded. So the always this RAM will change some data. Suppose you are having 11 programs which is running. So the RAM, what RAM will do, it will execute only 10 programs at a time, because it is having a maximum capacity of 2 GB. So it will be executing only 10 at a time, and it will send sometimes it will load, or it will stop running of one particular program and take another program from the memory location, from the hard disk, and it will run that particular program. So it will always, it may exchange data between this memory. In your mobile phone, it will be internal memory or your external memory card. So in this case, we are having this transfer of data will always occur between this RAM and HD, and the RAM will be running slowly because of this. Okay, so that is why we require more size for this RAM. Memory size, if you consider, RAM should have very large size if you want to get a very smooth operation, or if you want to use different applications, run different application at the same time. So in such cases, we need RAM with more memory. Okay, for example, if you are using a 4 GB RAM, which the your mobile phone or your computer system, then that system will be much faster than if you are using like a 2 GB RAM. Okay, if you are using 2 GB, the entire system, mobile phone or your computer, will be slow as compared to this RAM 4 GB if you are using 4 GB. So how much memory is there for this RAM? Depending on that, your system will be fast or slow. Okay, so for a given memory, the RAM can take some particular number of programs, and it can run that number of programs simultaneously depending on its memory. And if you are having the programs which is very large, number of programs is larger, and the memory which is required is more than the actual memory allocated for this RAM, then that will make the system slow, because one program, in this particular case, if you consider, if you are having these 10 programs, and each of those will take 200 MB memory location from the RAM, and then in such cases, if you are adding one more program and you want to execute 11 programs, then the 11th program has to wait in between sometimes, because already 10 programs are running. Okay, so there the system will be having some low operation because of this direct data communication will occur between RAM and this hard disk, because we are having 11th program. So one, for example, if you are using WhatsApp and then we are using let's say some Facebook something, or if you are using some other operation, so this we are having suppose 10 such operations, let's say some ABCD. Okay, so in that case, suppose let's say this is some this is taking this whole etc. So this is the 11th one, 11th one, this is 10th one, this is ninth application, and here are having first one. Okay, some next. Okay, so if you are running this 11th program, then what actually the RAM will do? It will run the first 10. Let's consider this first 10, and it will run, and it will give this data in between. It will store the data corresponding to Facebook into the hard drive, and it will execute this program. Okay, so at that time only 10 programs are running. Okay, Facebook is now which is loading. Okay, and if you are having some operation, if you have some operation in WhatsApp, and if the RAM has done something, and then it will send the data into the memory, into the hard disk, then it will choose this program to be running this too, for example. So it actually it will be running 10 programs at a time and one pending. Okay, and it will always communicate with this hard disk, so that the system will become slow. Okay, so we need actually we need a RAM, random access memory with larger in size. Okay, then the system, the computer or the mobile phone, that will be running very smoothly if you're having that system with more RAM. Okay, so that is the basic idea where we will have this application of this RAM, and this is nothing but the random access memory. You might have seen these pictures of this RAM. You can easily see that if you are opening the your CPU of your desktop, and there will be that motherboard. In that motherboard, you can see a very slim uh, board like this. Okay, I don't have that picture. You can write this, search for this. This like this, something like this, and there will be number of pins here with some edge, and there are, it is continuing, and you have some boxes like these. These are chips, IC chips. You can, so this kind of a device you can see. Okay, so it is a thin one like this. So that is the random access memory, and if you consider the RAM, it is also called as the direct access memory, because each of the memory locations in this RAM will be directly accessed. So it is also called as direct access memory. Okay, and here we are having this random access means each and individual byte in entire memory can be accessed directly. That is the meaning of this random access. So the random access means that individual byte in entire memory can be accessed, can be accessed, can be accessed directly. That's why it is also called as direct access memory. Okay, because each and individual byte of that entire memory can be directly accessed in this RAM. Okay, so it is used to store data and instructions temporarily, because when we are having the power, at that time only it will work. If you lose power, then it will lose its data. Okay, so otherwise we can call it as a volatile memory. Okay, it's a volatile memory. It is a volatile memory. Volatile memory means that content will be, or contents are lost when the power is turned off. So when there is no power, the contents will be lost. That's why it is called as volatile memory. So such memories are called as volatile memory. So the content will be there only when we apply the power to these memories. Okay, so basically this memory, because of this, these memories are used. Okay, this it is used to store data temporarily. Now, suppose if you do some writing in Word, for example, if you are using your system, okay, and you are working in a Word file, Microsoft Word, you are writing some letter or something, for example. So something you are writing here in your computer system or in your mobile phone or whatever it is, such kind of electronic system, if you are writing something and associated with that writing, for example, if you write some paragraphs, some lines, that will be stored in RAM. Initially that will be stored in RAM. So if suppose if you are not using any uh, this backup for your power, okay, if you are not using any CPU or something like that. And in that case, if the power is gone, then you might have came across with this kind of experience while doing something on the system. If your battery or if your power is gone, then that particular Word file, if it is not saved, you will lose the entire data. You will lose the entire data, and that is because your the entered data in that Word file, that will be stored in RAM, and that is stored temporarily. Why it is stored? Because it has to the CPU has to show you what you have entered at present through this monitor, and for that purpose, that particular data will be stored in the RAM, in random access memory. And if you are not saved that file, when you save that file, it will be stored in the hard disk. Okay, so basically when you're writing something, you will be storing that in the RAM. Okay, when you're writing something, at that moment it will be stored in RAM, and you will be having an icon on, for example, if you consider that Word file, Microsoft Word, you will be having something like this to save the writing, that whatever you have done here. So you have something you have written here. Okay, you wrote something here, and then you, if you press this save option, save button, if you press that save button, what is actually the CPU doing? The CPU will send information to the hard disk to save the particular content. Okay, So the CPU will find the memory location, all those things, assign some memory location in the hard drive, and save this particular data in that particular memory location in hard drive. Okay. Suppose if you are not saving the data, and if your power is gone, if it is power is off, suddenly something happened and your power is gone, and then in that time this data you cannot get back. When you switch on again, you will not get this data, because that data will be stored in RAM, and RAM is a temporarily memory location, temporary memory location. Okay. So that when the power is on, at that time only the data will be retained in the memory, in random access memory. But if you save that file, then that um, data will be stored in hard disk, and in hard disk it will be stored permanently. Even power is gone, the data will be there. Okay, that's why we have to repeatedly save. When you do any operation in your system, you have to repeatedly save the same document, or the operation, in order to avoid this kind of effect. Okay, this kind of uh, losing of your data because of the power loss. So this is what is we call it what we call it as a volatile memory, because the data will be there in random access memory only when the power is on. Okay, and if the power is gone, then the data will be gone. Okay, so that's about it. So it is a volatile memory, and these operations, all those operations will be so if you are writing this word file, something in that word file, so all those things will be, initially it will be stored in RAM, random access memory. Okay, so when it is stored in RAM, so this is stored in RAM, and RAM is connected to that CPU, and CPU will always take data. Okay, so once you enter the something in keyboard, suppose something in keyboard, if you enter and you are having the monitor here and you are working on with the word file, you press the letter A here in the keyboard, so corresponding binary number will be going to this CPU will understand it is coming from keyboard, and it has to show it is in the application word file. Okay, that will be understood by this CPU. Okay, and that CPU will send information to both RAM as well as to this desktop. Okay, so in the desktop, you have to get something like this A. When you press A button, A key on this keyboard, you have to get this kind of display in your monitor. So for that, CPU will send information to this monitor as well as it will be storing that particular data in RAM. Okay, so that is a temporary storage. So it is stored data, that is the letter binary value corresponding to this A will be stored in RAM as long as the power is on. Okay, and if you are not saving that particular file, if you are saving that file, then CPU will send the same data into the hard disk, and it will store in the hard disk. If you are not saving the data, then this entire data that you have entered will be lost once your power is off. Okay, so that's about the volatile nature of this random access memory. Okay, now if you consider the different types, basically we are having, when you consider your system, we'll be having 64-bit data, sorry, 64 bit memory. So this is 64-bit RAM. It can be 64-bit as well as the 32-bit data path. Okay, 62-bit or 32-bit data path. Okay. So this refers to the number of bits of data that can be transferred in a single clock pulse. If you consider, you will be having 64-bit or 32-bit system. If you consider any system, it will be 64-bit, either 64-bit or 32-bit, which means that the path 64-bit or 32-bit data path, which means that the number of bits, this is nothing but the number of bits transferred, number of bits transferred in a single clock pulse. Okay, so if you are using a 64-bit system, and or if you are using 32-bit, you will be transferring 64 bits per cycle, per clock cycle. And if you are using 32, then it is 32-bit, you will be transferred. Okay, so this both can work. Basically, we will be having these two types of system, which will be supporting 64-bit or the 32-bit. Okay. I think my cover is gone. Let me see my charges. Almost. It is not coming. Wait. Okay. It's working now. So we can have this 64-bit or 32-bit data path. So if you consider 8-bit, what is this 8-bit? 8-bit is nothing but 1 byte. 8-bit is 1 byte. Okay. If you do the math, if you consider RAM with, for example, PC 100, and this is just an example. If you consider a PC 100 RAM, okay. So which means that it is having, suppose this is having 100 megahertz is the speed at which it operates, this PC 100 operates. So this is an example for one type of RAM, PC 100, okay, which is having a so this much will be the bandwidth of this particular RAM, 800 MB per second. That is the bandwidth corresponding to that RAM. And there are different class of this RAM. Some RAMs will be in GBs. Okay, normally we use GB RAMs, right? So some will be in GB scale. This bandwidth will be in GB scale. So this is just a typical old RAM, which is having this 800 MB per second. Okay, PC 100. Okay, so I have just given you this math, how we can calculate that bandwidth of that particular RAM if you're having 100 megahertz of speed and 8 byte, which means that 64-bit. If the system is in 64-bit, if it is having data path which is equal to 64-bit. So in that case, we will be having a bandwidth of 800 MB per second. Okay. And this is how we can calculate that bandwidth. And if you consider the RAM, we have basically two different types of RAM. One is called as dynamic RAM, and the other one is called as static RAM. And now we will discuss what are the difference. We will classify them in the next class, but I will just say uh, explain what are these different types. So this dynamic RAM, dynamic random access memory, or we can call DRAM. And we have, this is the first one, and the second one is static RAM. Okay, so in dynamic RAM or DRAM, this is used in most of these computers. Used in most. This is used in most computers. Okay, so here these are built by these are built by using capacitors. So capacitors will be the memory elements here, and each of these capacitors store electricity and act as the bit of information. Each of these capacitors uh, uh, stores electricity. Okay, so this stores electricity or charge. You can say stores charge, and act as act as a bit of information. I'm talking about this electricity. This electricity or charge, they will act as a bit of information. So one bit of information is stored when you are having charged capacitor. Okay, I will explain the operation, working, all those things. Uh, uh, so here the these electric charges will be stored in these capacitors, and this charged capacitors will be acting as a bit which is equal to 1. If it is not charged, then it will be acting as 0. Okay, so that's how we will store the binary values in this dynamic graph. Now this electrical charge of this DRAM decreases with time because of this capacitor's decay. It cannot store the data for the entire time. There will be some decay for these capacitors. Because of that decay, this electrical charge which is stored in this dynamic RAM will be continuously decreased, and we will lose the data. Okay, so in order to prevent that, we have to continuously recharge or refresh these capacitors to maintain the data in the memory location. Okay, so that point also I will add here. So here we are having this electrical charges electrical charges in charges in these capacitors will be decreased over time, and the data will be lost. To prevent prevent this these capacitors these capacitors uh, has to be recharged recharged, or the better word is refreshed, because in sometimes it will be zero already. So we don't have to recharge that capacitor. So this zero, we do not have to recharge. Those which is having charge, only that particular capacitor we are going to charge. So better word is refreshed. So which means that it is retaining its state. Refreshing means whatever state it was, if it is charged, then we have to charge it. If it is not charged, then we have to leave that capacitors. Okay, so refreshed uh, capacitor has to be refreshed continuously to maintain. Okay, to prevent this capacitor has to be recharged or refreshed continuously. Okay, that is enough. Yeah. Okay. So basically that means, what that means, the dynamic RAM require an electric current to maintain the electrical state. Okay, what this means, this entire paragraph means that this DRAM require an electric current to maintain this electrical state. So in order to have that memory state, you have to constantly supply some electric current, and this refreshing will be controlled by an external counter. Okay, so it will be automatically controlled or automatically happen in this DRAM, and it is controlled by another um, circuit which will be having a counter. So that counter, depending on that time, how much the discharging is happening in this capacitors, that we have to calculate. And with respect to that, we'll be having something like a hold time. And with respect to that hold time, we have to recharge that, or we have to refresh that particular capacitor. Okay, and so that depends on the leakage or the uh, decay of those capacitors. So how much how fast they can decay. Okay, depending on that, the refreshing time or the hold time also, so that will change. So that will be depending on this capacitance. So this capacitance will be in femtofarad. That much of a small capacitors will be that. So then if you limit that capacitor value charge to some, for example, if it is some 70% of charges, so then you can take it as a logic 1. If it is less than that, it is taken as logic 0. So in that such kind of concept or logic, if you assign for that capacitor, and so then we have to consider when it is going to become less than that 70%. That time we have to calculate, that is the hold time of that particular capacitor, and that time you have to get, and within that time you have to refresh that capacitor or recharge that capacitor. So according to that, we'll be having some external circuits with the counter, and that will automatically done. Okay, that will be automatically done. Now we will discuss how this operation, what is the operation of this particular capacitor or the DRAM, how it can store these memories, that we will discuss now. Okay, so this DRAM consists of basically the capacitor transistor network. Okay, so let me see. if you consider this DRAM, basically the memory, one memory element, if you consider the transistor, so we can consider a transistor here. So basically, if you have a transistor like this, if you consider that MOSFET, then you'll be having a gate. This you have learned in the first module. Okay, so we'll be having this source, drain, and gate. So when your gate is having some voltage, if the gate is having voltage with this maximum voltage, okay, so when voltage is applied in this gate terminal, the current can pass through this transistor, which means that if your gate is having some potential, let's say some voltage we have applied here, then in that time this will be acting like a short circuit, as you have studied for the FET operation, so that this circuit will be acting as a short circuit and current flow from this source to drain. Current flow will be like this, and so it will be like a short circuit when you're having gate which is applied as some potential, and when the voltage is applied to the source instead of the gate, so gate does not having any potential, and in that case no current will be passing through this transistor. So when you're having this gate which is applied with the potential, and in that time this transistor will be acting like a short circuit, and current will flow from this source to drain. Okay, that is the basic operation or basic concept in this DRAM. And once you understood that, we can go to the cross section of this DRAM. So this is the only concept that you have to understand when you are having potential which is at this gate. Okay, you have some potential here, then this current will flow from this source to drain. Okay, so which means that this will be short circuited. When the gate current is zero, when this is zero, then we will not be having this connection in between, and this there is no current will flow from source to drain. Okay, so to make a memory cell, so this is a transistor, and if you want to make a memory cell, then you have to connect this drain terminal to the um, capacitor. Okay, so let's consider that. Then in that case, we will be having, let me see. So this is basic operation of the this transistor. And when you are considering memory, so we have the transistor element here. I will draw it a little below because we need more space in there. So let's consider this is your transistor. Okay, and this one will be connected to the capacitor. This is connected to the capacitor like this. So these capacitors will be acting as your memory. As we discussed earlier, the DRAM or dynamic RAM will be having these capacitors which will be storing electric charge, and depending on that whether it is stored or not, we'll be considering that as a state, whether it is 1 or 0. Okay, that will be considered. So this is the one memory element. Oh, so in this, 1 bit of data can be stored in this memory element. So this is connected again, this is connected to a line here, where I will use some different color for that. I will complete this. So we have this kind of n number of memory elements will be there, large number of memory elements like this. Okay, again this will also be connected to capacitor. And again we'll be having same in this row, etc. Similarly, we'll be having memory elements to this below also. To this here also we'll be having this kind of memory element. Okay, and again we are having here also we are having the same. And this also will continue below. So we'll be storing one bit of information in each of these memory elements, and we have thousands of or lakhs of these memory locations according to the memory size. So we have another two lines which we have to consider here, which are these two lines. One line going like this. Okay, that is nothing but word line. So this is the word line. Word line. Similarly, we will be having the same. Sorry, this one is bit. Okay, this is bit line. This one is bit line. This one will be bit line, and the one which is going in this way, which is the word line. Here also we'll be having these lines. Okay, so this will continue. Okay, this will continue, and let me see this. Okay, so here we are having this word line. This is the word line, and these are the word lines, and this is the bit line. This one is bit line. This is also bit line. This is the word line. This one. Okay, now how this operates, how it can store the data. We have basically three operation. One is write operation, second one is hold operation, third one is read operation. So we have three different operations here. I will complete this. So we'll be have, oh, this one will be grounded. Okay, this one will be grounded again. This one is connected again to the capacitor and grounded here. Now we will discuss the working, how we can do read, write and hold operation in this particular RAM, DRAM. So let us consider the first case, that is the write operation. So in the case of write operation, we have to store some data into the memory, that is write operation. Okay, so first we have to consider the word line. Consider the word line as one. Word line is WL, means word line. So this line is one, as you can see here. These lines are one, This line is 1, which means that you are getting a higher potential here in this line. Okay, 1 stands for maximum value or the high potential, and 0 stands for ground. So we are applying a higher potential here, which means that these transistors are in on state now. Okay, these transistors are in on state. So the transistors are on. Okay, so then what will happen? So now the current can flow through this path. Okay, and according to this bit line, whatever value of this bit line, your capacitor will be charged or discharged. Okay, so for example, if you consider the bit line is having value 1, which means higher voltage, or which is equivalent to VDD. So which means that this is having higher potential now. Bit line is having at high potential. So this bit line will be, for example, at 5 volt. Then this that particular voltage will charge this capacitor. Okay, this capacitor will get charged. So let us consider the bit line as 1, for example. Bit line is equal to 1. You can also put bit line equal to 0. So bit line can be considered as 1 or 0. If 0 means it is grounded. Okay. So if it is grounded, then the capacitor will be discharged, and all the charge in the capacitor will be discharged through this path. Okay. And the charge inside the capacitor will become 0. Or if the bit line is 1, that is the high potential, or it is equivalent to VDD. In that case, what will happen? Then this capacitor will get charged, and that will become fully charged. Okay. In that case, if the capacitor is fully charged, then it is corresponding to the state 1. Okay. So the capacitor charged or discharged. Okay. So it depends on the state of the capacitor. If it is already not having any charge, then it is not discharged. Okay. But if it is initially it was in 1 or the fully charged state, then it will get discharged also. So that is the operation for write operation. Okay, that is the working corresponding to write operation. So we have to consider the word line as 1, so that the transistors are on, and then you consider bit line either 1 or 0, whatever you wish to enter into the memory. If it is 1, then bit line has to be 1 or the higher potential. Then the capacitor will be charged, and the corresponding capacitor will be having a charge which is equivalent to the state of 1. Okay. If you want to store 0, then this bit line has to be connected to ground, and if the capacitor is initially charged, then that will be discharged, and capacitor charge will become minimum, and in that state that can be considered as 0. Okay, that is how we will write or we store any data into this memory, dynamic memory. That this process is called as write operation. And the second one is read operation. Read operation. So for read operation also we need this word line which is equal to 1, word line equal to 1, and consider the word line equal to 1 means again transistor is on. Okay, and your bit line will be like some VDD by 2, that is the maximum potential by 2, and we actually assess the trend here, what will happen to this bit line. So we will be having an additional sense amplifier along with this transistor. We will be connected with this bit line will be connected with the sense amplifier, and the sense amplifier will test whether it is the charge is decreasing or increasing. Okay, so according to that we can say whether it is in state 1 or 0. So that is how we will read the data. Okay, so if the VDD by, if we consider bit line is equal to VDD by 2, so which means that we are considering here the voltage as VDD by 2, and this, if this capacitor is fully charged now, that is in the state 1, which is VDD, then what will happen? This line, bit line is VDD by 2 now. So let us take another color. So this is VDD by 2, VDD by 2. So what will happen? This capacitor will starts to decrease its charge, because here it is low potential, here it is 1, which is VDD. So the capacitor starts decreasing, and this sensing amplifier attached to this bit line, that will sense that uh, this capacitor is decreasing in its charge, or this here the potential is getting increased, charge is getting increased. So the capacitor, this by using this sense amplifier, we can say that the capacitor is charged, or the state is 1. Okay, now consider the capacitor is having state 0, or the capacitor is not fully charged, or charge is minimum. Then in that case the state is 0. Okay, then what will happen? This VDD by 2, from this portion the charge will flow to the capacitor, and the capacitor starts charging, so that the VDD by 2 potential decreases. Okay, and that will be read by this sensing amplifier, and we can say that the decreasing trend in this bit line, so that we can say the capacitor is not charged fully, and correspondingly the state is 0. Okay, so according to that the state of the capacitor, we can understand the state, the memory, whether it is 1 or 0. Okay, so bit line we are considering as VDD by 2, and then by sensing amplifier we can understand the state of capacitor. Say state of capacitor means this is same as that of the stored data, whether it is 1 or 0. So that is the read operation. And the next operation is hold operation, the third one, which is hold operation. And in this hold operation, what that means? Which means we have to hold the data which we stored in this memory, in dynamic RAM. So in this case we are considering the word line which is equal to 0, which means that the transistor is off. So the bit line cannot be connected directly to this capacitor, right? So when your this transistor is off, which means that we are considering this word line equal to 0. So the transistor is off, so the bit line cannot be connected to this capacitor. Okay, so in such a way that we will protect, or we will hold the state of this capacitor. That is how we can make this hold operation. But there is a problem in this hold operation, because we are storing or we are considering the data, whether the memory as 1 or 0. What we are considering here, we are considering the charge of this capacitor. Okay, whether it is above some limit or below some limit, that is what we are looking into, we are considering, corresponding to the state 1 and 0. Okay, but when you are considering this capacitor, okay, there will be always leakage, always there will be a discharging. leakage current will be there, and there will be discharging, and because of that we will lose data. And for each of this leakage, or if for this discharging, we have to refresh this capacitor, or the memory. Okay, we have to refresh the memory, which means that we have to recharge this capacitor after a few milliseconds. Okay, and there will be some counters that will be doing all these processes, which will be measuring how much time, with what time we have to refresh or we have to recharge this capacitor to get its original state, to retain its original state. So there are some additional circuits to ensure this state of this capacitor, or the charge inside this capacitor. So after a few milliseconds we have to refresh. After every milliseconds, some few milliseconds, we have to recharge this capacitor. So we have to read this capacitor, what is its charge, and then we have to uh, refresh it again and again. That's why it is called as a dynamic RAM. It will change its state, okay, every time, and we have to recharge it or refresh. This process is called as refreshing. This process is called as refreshing. Okay, and as we discussed, for example, the state, initially the state of the capacitor was 1, then it will be discharging due to leakage current, and it will become 0 state, which means that it is not completely discharging. For example, if you consider above VDD by 2, if you consider that as 1, and below VDD by 2 if it is considered as 0. So if it is above VDD by 2 or VDD by 3, sorry, not VDD by 3, some 3 by 2 of VDD, something like that, then we can consider it as, if you are considering it as a 1 in the high state, then we can say up to this time, if you consider this from 1 to 0, it will take this much of time, it is taking. Then let us say up to this, about this value of time, let's say t1. So 0 to t1, within this 0 to t1 time, it will be going below the level that is corresponds to the high state. Okay, then we have to refresh it again. We have to recharge that capacitor to its maximum level again. Once it reaches this state, again we have to go to this the high state. Okay, so this refreshing has to be happened in within a very few milliseconds, and this will be done automatically by using some additional circuits, including counters. Counters will determine with what time it has to be refreshed. This capacitor has to be recharged again. That's why it is called as a dynamic RAM. It will change state every time, and we have to recharge it again and again. Okay, so that is the problem associated with this dynamic RAM. Okay, so that's the whole process or operations associated with dynamic RAM, and we will discuss the static RAM in the next class.